Assalamualaikum. I'm Adhere Hussain, a PhD scholar at Islam School of Mathematical Sciences. I am working under the kind supervision of Professor Abdul Professor Abdul Mikbar. Control L. Actually, I think Dr. Sarmad has explained deeply the importance of differential equations to model real-world phenomena. And I will continue the same domain. And we will discuss a method that is based upon the exact solutions or the analytical solutions for the difference equation. So we will start. Here is the title of my talk is the invariance, conservation laws, and integration of difference equations. So here is the outline. First of all, we will discuss the introduction, and then there are some summarized results and basic facts are summarized in introduction, and there are some advanced definitions that leads to lead theory for the difference equation, and then we will use this theory to a problem, and at the end there are conclusions. So next, before starting. Or starting with the theory for the difference equations, can we imagine how do difference equations originate? So we have mentioned three sources here. While dealing with the number theory problems, like this is a classical Fibonacci sequence, and there are some other sequences as well. All these are examples of a difference equation. And then while solving differential equations using power series method, like we solve a second order differential equation with the power series method, then we come over this recurrence relation. This basically provides us a difference equation. And number three, we have noted by the discretization of the differential equation. Like for example, we discretize here the time independent Schrodinger equation, and we discretize this with the implicit scheme. The approximations for the point and the derivatives follows from 2, 3, and equation 4. And we insert the values in given equation, and we have the expression in 6. And we introduce some constants, and we have the difference equation that is in 8. And here the function we have used defines the non-linearity of this difference equation. So these were some main sources for the difference equation. Now I would like to summarize some results that are the symmetries for the differential equations. Here, the theory and reasoning for the construction of symmetries of the differential equation is now well established and documented. Moreover, the application of these for the analysis of differential equations, particularly for finding exact solutions, is widely used in a variety of areas from relativity to fluid mechanics. Secondly, the application of these, secondly, the relationship between symmetries and conservation laws is of much importance since Noether celebrated this work for variation of differential equations, and then this was extended by some others that were Blumen and Enko. And the first consequence of this interplay has led to a double reduction that was done by Shajabai, and then that was generalized to multi-reductions. Now we have some remarks for the symmetries for the difference equation. So a vast amount of work has been done to extend the idea and applications, symmetries to the difference equation in a number of ways. In some cases, the difference equations constructed from the differential equations have the same algebra of least symmetries. As far as the matter of conservation laws, the work is more recent. So what we will do here we will discuss the symmetries for the second order difference equations, and then we will use them for the reduction of the equations, and then we will discuss an algorithm to construct the first integral, and then we will check the relationship between first integral and symmetry generator. So now we first start by considering an nth order difference equation, that is given in 9. Here W is a smooth function of its arguments of u, and the integer n is behaves like an independent variable. So as like differential equation, the solution of equation 9 depends upon n in arbitrary constants, and it is given as given in 10. Next, we define some invariants. That is, first we define our shift operator that maps n to n plus 1. And if we are given with the solution of a difference equation solution UL, then it will map U to UN plus 1, and similar way it can be defined in a general way. So now we summarize this. If we have a differential equation and our differential equation, then the symmetry generator for this ordinary differential equation is given as, and where xi and eta are the infinitesimals. Now we can, in a similar way, we can define this symmetry generator for our difference equation here. For a difference equation 9 and for a difference equation, we can define this symmetry generator that is given in 16 here, and these satisfy this symmetry condition 17, and where Q is the characteristic of one parameter group. For here, we are only interested by the second order difference equations. So for the second order difference equation, the symmetry condition follows in equation 18, where x is the symmetry generator given in 19. So now we define the first integral, that is basically if I the first integral, that it must be invariant under the action of a the operator. That is, we apply operator on this, and it remains same in the form of argument. This definition is given in 20, and for the next we define a methodology for the construct first integrals for the second order difference equation. So the definition of first integral follows in 21, and to construct first integral we define these two functions, and we next we used differentiations, and we follow the relation for P1, and in the same way we can have the relation for the P2, and these two functions P1 and P2 satisfy this first integral condition that is given in 26. I need 10 minutes. So such that the integrability condition is given in 27, and the integrability condition that is old, that is 28, given in 28. So hence we have the first integral that is given in 29. Next, for the reduction purposes, we have symmetry generator, and we consider an invariant, and that satisfies this invariant condition. And from the invariant condition, we can use the method of characteristic that is given in 34 to find the invariants, and these invariants can reduce our original equation by an order. So next we apply this theory to a problem like we consider here second order difference equation that is given in 39, and we apply the by the symmetry condition we follow this relation, and this equation has is difficult to solve because it contains three arguments of the characteristic Q. So we apply the differential operator on this equation, and differential operator on this equation, then we get the relation for, we get this relation. We apply this differential operator on this equation, then we have this linearized equation that is given in 4.2, and we solve this for the characteristic Q. We have the characteristic in 4.3, and thus we have this symmetry generator. Now, how we can choose this symmetry generator? We can use this symmetry generator. Next, we first construct the first integral with the same steps. We define two functions and the first integral condition, and using again this symmetry finding algorithm, we can find P2, and we can define P1 as symmetry condition, and same we can find first integral 5, that is given in equation 50. Now we can check the relationship between symmetry generator and first integral. That is, we can check, we map this symmetry generator over the first integral, and we can see that this vanishes. So this can associate that we can deduce that the symmetry generator X and the first integral are associated. So now for the solution for the reduction of the equations, we use this symmetry generator by over the invariant Vn, and we use the method of characteristic to get to these two invariants, and we can reduce our given equation to this equation 61. So next. So these are the references. These are the some references, and these are the some references, and this work has been published in this paper. So one can follow these.